Hi guys, today I'm going to be talking about integration, specifically approximating the area under a graph. So integration is a math methods topic in Unit 3, Area Study 4. The learning intention of this video is that hopefully by the end of the video you'll be able to use the left point estimate and the right point estimate to approximate the area under the graph of a function. So estimating the area under a graph. The graph of any continuous function between the interval of a and b on the x-axis can be estimated by dividing the interval into n equal subintervals. So here is a graph, a continuous function y equals f of x, and if we are trying to work out the area between the interval of a and b, we can divide the interval into n equal subintervals, or n number of rectangles, and then working out the area of each of these rectangles and adding them all up to get an approximation of the area. So once we have been given the number of equal subintervals, or sometimes we can choose it, depends on the question, you might be given it or you might choose it. From there we can work out the width of each of these rectangles, or delta x. So delta x is determined by subtracting the initial x coordinate by the final x coordinate of the interval, and then dividing it by the total number of rectangles or subintervals. Sometimes we are given delta x instead of n as well, and then we can work out n, or the number of rectangles, using this relation here. So for example, if we want to find delta x over the interval of 2 to 6, given the number of rectangles, or n is equal to 8, we can work that out by subtracting the initial interval from the final interval, which is so 6 minus 2 over the number of rectangles, or the number of subintervals, 8, and that just gives us 0.5. So that would be a rectangle width of 0.5. So once we've got the width, we can determine the area of each subinterval by using the left point or the right point estimate. So I'll go over those in just a second. And once we've got the area of all the individual rectangles, we can find the total area by the summation of all the individual rectangles' areas. So the left point estimate is an estimate using the left x value of the rectangle to determine the height of the rectangle and therefore the area of the rectangle. So using the left point estimate, we start at a. That is our initial value. So here a is equal to x0. So we'd sub in x0 into the function to determine the y value at this point, and that y value corresponds to the height of this first rectangle. So we can just then simply multiply the height by the width, which is delta x, which we determined before by this relation here, and work out that first area of the first rectangle. And then we do that for all the following rectangles. So the next one would be x0 plus delta x, then you add delta x again, so add the width, and so on until you get to the last rectangle, and you use b minus delta x because it's using the left endpoint of the rectangle. So this is the general formula of the left endpoint estimate. So you can see it's just multiplying the width of the rectangle, which is delta x, or b minus a, over the number of rectangles, and then timesing it by the summation of all the heights, starting from x0 and going all the way up to x of n minus 1, which is this one here. So using the left point to work out the height. The right endpoint estimate, on the other hand, is using the right coordinate of the rectangle to determine the height of the rectangle, and therefore determine the area. So this is the general formula of the right point estimate. As you can see, it starts at x1, which is this point here, and it goes up to xn, which will be the value of b, so the end interval. And as you can see from these graphs here, for a function increasing over the interval of a to b, the left point estimate is going to give you an underestimate of the area, and the right point estimate is going to give you an overestimation of the area. And on the other hand, a left point estimate for a function that's decreasing over the interval of ab is going to give you a overestimate of the area, and that is because the left point estimate uses the left coordinate to determine the height of the rectangle, and for a function that's decreasing over the interval, the left coordinate is going to correspond to a higher y value, whereas the right endpoint for a decreasing function is going to correspond to a lower y value, and it's the opposite for a increasing function over the interval. So we'll do an example to hopefully give you a better understanding of the process. So to find the approximate area of under the curve of f of x is equal to x squared plus 1 over the interval of 0 to 2. So first we'll use the left point estimate to determine the approximation. So I've decided to use an n of equal to 4, so 4 number of rectangles. If it's not given to you in the question, you can just choose. Just keep in mind that the more rectangles you decide to use, so the thinner they'll be and the better the approximation will be, but the more calculations you'll have to do, so the longer and more complicated the process. So for simplicity, I've just chosen n equal to 4. So once you've chosen or been given your n value, you can work out the width of the triangle using the relation from earlier. So it's just delta x is equal to b, which in this case is 2, and a is equal to 0. So b minus a is 2 minus 0 over n, which we've decided is 4, gives a rectangle width of 0.5. So once we've got our rectangle width, we can work out the rectangle height as well, and then the area. So for the first rectangle here, we are using the left point estimate method. So we're going to use the left point to determine the height of this first rectangle. So the x value of this point is 0. So we're going to sub 0 into our function here to determine the y value at this coordinate. And that gives us a value of 1. So that means that the height is, for this rectangle, is just 1. So to determine the area, we just multiply the height, which is 1, by the width, which is 0.5, and that gives us a total area for the first rectangle of 1. And then we go to the next rectangle. So the left-hand point corresponds to an x value of 0.5, and when we sub 0.5 into the function, we get a y value of 1.25, and if we multiply 1.25 by the width, which is 0.5, we get an area of 0.625 for the second rectangle. So the same thing for area 3 and area 4. If we sub in the left point of the third rectangle, we will get a value of 2 for the function of x, which corresponds to a value of 2 for the height of this rectangle. If we multiply the height by the width, we will get a value of 1 for that area. For 4, the height of the rectangle corresponds to a value of 3.25 when we sub in 1.5 to this function. And then if we multiply 3.25 by the width, which is 0.5, we get an area of 1.625. So to get the total area under the graph, we sum the areas of the rectangles, and that gives us a total approximation of 3.75. So for the same function, f of x is equal to x squared plus 1 over the same interval, 0 to 2, if we want to use the right point estimate, using the same number of rectangles, so n is equal to 4, we will repeat the process, but we're going to be using the right endpoint of the rectangles to determine the height instead of the left endpoint. So you can see that it's going to be an overestimate because the right endpoint corresponds to a higher y value, which gives us an overestimate for all the areas. So if we go through the process again, we'll get a value of 0.5 for the delta x, because it's over the same interval and we're using the same number of rectangles. And then to get the areas of the rectangles, we sub in the right endpoints because we're using the right endpoint method. So we sub in the right endpoint of the rectangles into the function for x, and we get the value for the height, which corresponds to the y value at that point. So for area 1, it's we sub in 0.5 to f of x squared plus 1 for x, and we'll get a value of 1.25 for the height. So 1.25 times the width of 0.5 is going to give us a total area for that rectangle of 0.25. We do the same for the other 3 areas. So we sub in the right endpoint, so that corresponds to x is equal to 1, 1.5, and x is equal to 2. We will get the heights of 2, 3.25, and 5. So to work out those areas, we times the heights by the width, which is 0.5 for all of them, and we will get a height of 1, 1.625, and 2.5, which gives us a total area, once we add each individual rectangle together, this is a total area approximation of 5.75. So we can see that the right endpoint estimate gives us a larger approximation of the area. So hopefully this video has given you a better understanding of estimating the area under a graph. My final tip would be to try evaluating the area under the curve for yourself. And if you need any extra examples, check out openstacks.org. It's a free resource and it's got a heap of really good examples, not just for calculus, but for all the topics for methods. And good luck, hope this has helped.